Hello, it's Keith here, and this is lesson 37 of the platform-specific series of my 68,000 assembly programming tutorials, and we're looking at the Amiga again today, and we're looking at the BLITter. The BLITter is a memory block copying piece of hardware that can work separate to the main CPU, so it's faster, and the CPU can do other things at the same time, and we're going to be using it to draw sprites, and you can see some of those sprites up there. The other thing we're going to be looking at today, though, is an alternate memory layout for the screen. Now, in the past, we've been working at it always in bitplanes, but the bitplanes have been done as blocks, so an entire block of bitplane 0 for all the pixels, then bitplane 1, then 2, and then 3. Today we're going to be doing it differently, and we're going to split by lines. So we're going to have 40 bytes that are a line of bitplane 0, followed by 40 bytes which are the same line bitplane 1, followed by 2, followed by 3, and then the next line of the screen. The reason we're doing this is the BLITter can work with a block of a certain width and a certain number of lines, and by doing this we can get the BLITter to copy all 4 bitplanes with one super tall copy, and that's what we'll be doing. So we'll be looking at both of those things today. Now, about the BLITter. So basically the BLITter is controlled pretty easily. We've just got a series of addresses that represent different parts of the BLITter configuration, and we'll be looking at all of those. The BLITter itself has a total of 4 different DMAs, and 3 of these are sources. We can use 1 to 3 of those sources, and the number we'll need will depend on the kind of operation we're doing, and there is 1 destination, and these are marked A, B, C and D. Now, in the simplest operation, which would be a sort of a P set, replacing anything in the background, the source would be A and the destination would be D. If we're trying to do something more complex, like an XOR, which is inverting the current background and replacing it, or a masking operation where we are keeping the background, using a mask to remove the background and using a graphic color to put over the top of that, then we would be potentially using all 4, 3 sources and 1 destination. The combination of those is done by a logical operation known as a minterm. Now, this isn't a piece of terminology I'd heard of before, but apparently it's a real thing. There is a document on Wikipedia. If you go to my website, you can get the link for that, and you can read all about minterms until your head explodes. But in simple terms, we need to give the Amiga a byte, which is a logical operation on how to combine these possible 3 sources into 1 destination and draw to the screen to make the effect we want. Now, there will be multiple ways of getting the same result using different combinations, and so I'm showing you a few here that I've used. I'm not saying they're the best, I'm just saying these work and do what I wanted. And in these charts we're looking at here, then the exclamation mark I'm using represents a not, which is where we flip the bits. The multiplication is effectively an AND of the bits, and a plus is effectively an OR. Now, the not symbols I'm using here was just for convenience of the ASCII character set. You often see this is represented as as a line above the numbers, but you do always see this multiplication and this plus for combining them together, which, as I say, is more logically in my mind an AND and an OR. So we're going to be looking at a simple one, which is a P set, which is F0, and this is where the destination is just equal to the source. That we're going to be looking at a masking operation, which is CA, where the destination is set to A, where B is set, or it's set to the background, where B is not set. Now, the final one we'll be looking at will be an XOR, and this is where the destination is set to the opposite of the bitmap data, where the background is set, or the bitmap data itself where the background is not set. And you can see here that basically we've got a set of different possibilities here. Our destination can be set to the A source or the not A source, the B source or the not B source, or the C source or the not C source, and then what we can do is we can add permutations and combinations of these together, or we can multiply them. And so through various combinations of A, B and C multiplied or added on or inverted with the not, we can build our mathematical operation which is going to produce the resulting bitmap data. I'm not going to lie to you, this absolutely blew my mind when I started looking at it, but hopefully you can at least use the sample ones I've given you today, and the best thing to do is just have a go and basically try and use these template ones where you can. These were transferred out of a book, but if you want to get really more advanced, then you can do. Now, in a lot of cases, the logical operation you're going to want will not be in this list. You might want something more complicated, but basically you can combine multiple together with an addition type effect by ORing the two values together. So for example, if we want to create the minterm d equals a plus not b, well, a is f0, b is 33, so ORing those together gives f3. And if we want to multiply them together, we can do that by effectively ANDing them together. So d equals a equals f is f0, d equals c is aa, so d equals a times c will be a0 from that ANDing operation. But anyway, as I say, if you don't understand these minterms, which I totally understand because they did confuse me, basically you can, just use these kind of stock ones you can get, and as I say, just try it out and you'll hopefully get the result you want. Now, when it comes to setting up the BLITter to do a job, basically there are a set of registers we need to set. Now let's go over to our source code and let's actually discuss what we need to do. So the first thing we're doing is we're setting up our screen. Now the screen memory is defined in exactly the same way as before. We're defining a block of memory of the same size as always. The only difference now is the way we're defining that memory to the hardware. Now as before, we're defining the 4-bit planes in memory, but this time we're separating them by just 40 bytes, so that all 4 of the bit planes are 40 bytes separate. Each line, a single bit plane, is 40 bytes because it's a 320 pixel wide screen. So it's 160 bytes for one line of all 4-bit planes. And this means that there's effectively 120 bytes after each bit plane to get to the next line of the same bit planes. So you've got bit plane 0 line 0, then you've got bit plane 1 line 0, then bit plane 2 line 0, and then bit plane 3 line 0, and these are all 40 bytes apart. So bit plane 0 line 0 and bit plane 0 line 1 are 160 bytes apart, and that means that we need to skip 120 bytes after each bit plane line, and we're setting that in the BPL mod 1 and 2. Those two, one's used for odd bit planes and one used for even bit planes, and we need them both to be the same. So that sets up the screen. Now we need to give our program the sprites in a different format. Before, what we were doing was we were transferring all of the bit planes separately. Well, now the job for each bit plane is exactly the same. We're just transferring bytes. The difference we have to change is we need to transfer 4 times the number of lines vertically. So we're multiplying the height by 4 here, so our sprite is 48. We're multiplying that by 4 because we need to transfer 4 times the height for the 4-bit plane lines. It's a much easier operation. It's just 4 times the height, and that's why it works so well with the BLITter. Now, we do need to export our sprites in a different format. As always, our Sprite editor has been upgraded to do the job. So if we go to the 68000 option, Amiga, we've got these new options: Save Raw Bitmap, Interleaved, and that's what you need for today's example. So that's how I exported the graphic for today. Now this code here will do a software sprite. What I have added, just for clarity here, is I've done a bit plane shift. I've actually shifted the destination data, and that's causing the sprite to come out in a different color. You can see this weird inverted chibico back here. That is a bitmap, a software sprite, which is not really what we're interested in today. What we want to look at is using the BLITter. Now, the first thing we need to do to use the BLITter is we need to turn on the BLITter's DMA, and we're doing that with bit 6 here of DMA con. We're turning that to on, setting it to a 1. That enables the BLITter. What we do next is we need to calculate the destination address for our image. So I'm using get screen pos here, which is a routine I've used in the past. This takes an XY position and it returns the destination in A6 of the VRAM. So what we do next is we set some of our registers. Now we need to set a variety of them. So basically the ones we'll need to set will vary depending on the task we're doing. So you can see here we've got multiple sources and destinations for our 4 possible BLITter functions. So we've got C, B, A and D. Now D is always the destination, so that's going to be our screen. A, B and C will be sources what they are depends on the kind of mathematical operation we're doing. The mathematical operation is set in BLITcon 0. It's basically the bottom byte here. A, B, C and D are the 4 possible DMAs. That's the sources and the destinations we may need to turn on. We can also apply a bit shift to source A and also a bit shift to source B in BLITcon 1 here. BLITcon 1 can also do filling operations, although that's not something I'm covering here. There are even more clever functions though. We can also effectively achieve a bit shift for the source A. This allows us to bit shift by individual pixels the sprites that we're showing to the screen. The BLITtter works in words, so this allows us to basically shift by 1 to 15 pixels, and it's very fast. So this is how we can shift by individual pixels and not be limited to byte or word offsets for drawing our sprites to the screen. We can also set modulos for the sources and the destinations, and we'll need to do that to skip data if we're writing to the screen to make sure we move down a full line. And also if our source, one of our sources, if it's the screen, if we're using the screen as for an XOR or something, we'll need to set that. We'd want to set that to 0 if we're doing our sprites, though usually, at least in the format I'm using. Now the final thing we want to do is we want to set BLT size, because quite surprisingly setting this actually starts the operation, assuming we've enabled that DMA. So we specify our width in word and our height in lines, and that will start the operation. All very confusing, I know, but hopefully you'll be able to just download my example and have a play with it. Okay, so what are we doing? Well, we're setting our source as the bitmap. We're setting the BLITtter source A pointer here. We're setting that to the long address of bitmap. We're setting BLITtter destination D to A6, which gets screen pos calculated for us. And then what we're going to do is we're going to set up the BLITtter. So we're only using one source here. So we're setting our min term to F0, which is just D equals A, destination equals source A. So that's just going to copy our source bitmap to our VRAM destination. We're setting A as enabled, the source, and D as enabled, the destination. D is always enabled, really. And we're setting no bit shifting, and you can see the bottom 8 bits there are equal to F0, which is the min term D equals A. We're then setting BLITcon 1 to 0. We don't need it. We don't really need any functionality of that for this. We're setting the mask of our routine to just fill the entire sprite to the screen. And then we're setting our BLIT size here. Now our width is 3 because it's 3 words, 6 bytes, 48 pixels. Our height is 192. Why 192? 48 lines tall times 4 bit planes equals 192, and writing to that BLIT size starts the drawing operation. So let's fire up our emulator again. So that will be the first one we see when we start our program here. So that's the PSET one we just drew. That's an alternate XOR one we'll look at in a moment. That's another example that was just bit shifted. That's the software one, and that's a blitted one with a mask. You can see the background shows through in the unused areas there. We're going to have a look at those other ones right now. Okay, so that's how we can do a PSET sprite. Well, what about an XOR sprite? Well, an XOR sprite will combine the bitmap data with the inverse of the bitmap data where the screen is already set. And so the min term I'm using for that is 5A, not A times C, plus A times not C. This is effectively inverting the source and the destination together. So we're using C as well. C is going to be the screen data as it currently stands, and D of course is going to be the destination, and A is going to be the sprite. So you can see that here we've done get screen pos again to get our bitmap destination. That's our VRAM. We've got our bitmap source here, which is BLIT pointer A. We are setting the destination as BLIT pointer D, and we're also setting BLIT pointer C as the screen memory as it currently stands for that XOR operation. We're then setting A, C and D as enabled. We're setting that logical operation there, the min term. We still don't need any settings for BLITtter control 1. We're not using the masks really, they're just all pixels shown. We are having to set an offset for our destination and our screen source. We're setting that as 34. That's basically the number of bytes after the end of a line to the start of the next line. I should have mentioned that on the last one actually. We did have to set that before as well. Sorry, I missed that there. So we're setting the BLIT source mod for the source sprite to 0 because the lines are consecutive in that source data, but the screen destination and the screen source in this example, we have to skip the unused bytes of the screen. The sprite is 6 bytes, the screen is 40. 40 minus 6 is 34, so that's why we're setting that accordingly. And again, we're just starting up the operation there. And the result is this XOR here. You can see that second sprite has been XORed over the first one. So where the two overlap, the result is inverted. Where the two don't overlap, the result is shown normally. So that's how we can do an XOR. Now, we've got another example here. This here is just another basic copy. It's set with no special effects here. But what we do after that is we're doing a shifted one. Now, this one's a bit of a pain. So basically, we are now effectively increasing the size of our source sprite here. Now, the reason we're doing that is we are going to effectively remove some of the pixels and shift the sprite, and that means that some of the pixels from the first word read in will actually be shown in a word after the last word, if you see what I mean. And so to do that, we're increasing the size of our sprite, and then we're correcting the source data, moving back one word after each line of the source sprite. The sprite being shown to the screen is effectively 2 bytes larger, so our offset for the screen, the BLTD mod, is 2 bytes smaller, now 32. And we're setting our mask for the data shown for the first and the last word of the sprite, so that some of the pixels of the first word are being hidden and most of the pixels of the last word are being hidden as well. And the reason for that, the last word being hidden, is it will actually, if we showed those, it would actually be showing extra data from the next line of the sprite. I'll just show you if I just enable this one here and I run this again. Now, I believe it is actually possible to bit shift the second source B as well with these bits here, although that's not something I've actually tried. Now, you can see here, I've left this enabled. So basically, this has caused some corruption to be shown. You can see all of these pixels that are weird where they come from. Well, they're actually the extra data. They're effectively the next line being loaded in because I've not masked those out, and I'm showing a sprite that is 8 bytes wide when my source data is actually only 6 wide, and the reason it's being expanded to 8 is because of that bit shift. The bit shifting is a bit of a pain, unfortunately, but it's so powerful you can't really complain. I am planning to do a clipping example where a sprite will be clipped at the edges of the screen and things, and that will be done with the BLITter on the Amiga. So if you stick around, you will see an example of how to use this in more convenient code, shall we say. So yeah, as I say, I know this is a little bit complicated, but there you go. So the next example was a CPU job. So this is not using the BLITter in any way, just using software. So if you want to use software, you can still do it with this alternate screen format. The final one is a masked sprite. Now this is, again, as always, created with Acro Sprite Editor. There are basically 2 files now. One is a 16 color sprite, which looks something like that, and the other one is a mask. Now the mask is being saved as 16 colors again, and it looks something like this. So basically the background is being set as white here, and the data that was being used by the sprite, which was effectively originally, the way Acro Sprite Editor works is you can basically use color 17, this pink here, to define areas as being transparent, and then there are various functions to export that transparent color separately. And so what I did in this case is I enabled the transparent mask here, and then all I did was I went to 68,000 Amiga, and then I saved a raw interleaved 16 color bitmap, and that was what I did. We're then importing that as a second layer, a second sprite here, transparency here. That's what I exported. And then we're using that as an extra source in this example. So this transparency effect is being achieved by basically using the destination as the screen memory, source C as the screen memory, the transparency as source B, and the bitmap as source A. And our logical operation is destination equals A plus not B times C. So not B is the mask for the background, and A is the bitmap data, and C is the current screen memory. Now, if your mask was in a different format, you might want to use a different operation. As I say, these min terms, there are many different ways of achieving the same result. So again, I'm not saying this is the best one, just that this got the effect that I wanted. So again, we're specifying our source memory here. We've got our bitmap as source A, our transparent bitmap as source B, our screen memory as source C, and destination. We're not doing any bit shifting again because I don't think my mind could cope with it another time. We're setting no offset for the mods for A and B. A is of course our sprite and B is our transparency mask for our sprite. C is the screen memory, so 34, again that's 40 minus the 6-byte wide sprite. And D the destination, again the same. We're then setting our size and that starts the operation, and this is the last sprite that we show in our example here. So if we just start this up here. So that's our PSET, that's our XOR, that's our bit shifted there, that's our software sprite, and this here is our transparent one. And you can see around the Chibico fireball there, you can see the software sprite showing through, and I think maybe you can just about see there as well around that building there. So as I say, the mask does indeed work, and it's a hardware sprite that has done that. So a little bit complex, but a very powerful, impressive function of the Amiga. Interesting to note, I was doing some research and the Atari ST did add its own BLITter later on, but the original Atari STs didn't have it, which the Amiga, I believe, did. So, you know, major points for the Amiga there. Amiga, a little bit of a pain in some places. I do prefer the X68000 in a lot of ways, but the Amiga is undeniably very powerful. So there we go. That's all we're covering today. I hope you've liked it. As always, go to my website, download the source code and the build scripts and all that kind of amazing stuff and have a play with it, and I'm sure you can do a better job of it than I can. If you enjoyed today's content and you want to support my channel and see more stuff in the future, you can buy my book. You can get my amazing programming book. It's called Learn Multi-Platform Assembly with Chibi Akumas. It's available on Amazon. It covers Z80, 6502, 68086 and ARM. You can also become a Patreon and you get the videos earlier if you do, and I pay more attention to your suggestions and recommendations and things like that from the paying backers. So very much thanks to them. Anyway, I hope you've enjoyed this today. Thanks for watching and goodbye.